Welcome to today's Explainer. We're jumping right into some seriously fascinating new research that tackles a massive headache for anyone building enterprise AI apps. I mean, analyzing a single document? Easy. But an entire enterprise's worth of data? That's where things get wild. Today, we're breaking down BatchDAG, an architecture recently dropped in a new arXiv paper and highlighted over on Dudarik.com. To really grasp why this is such a game changer, let's picture a scenario that literally strikes fear into the heart of every data engineer. Imagine you're tasked with building an AI app to analyze 50,000 enterprise meetings. Maybe you need to figure out if your account executives are asking good discovery questions, or how stakeholders negotiated price across thousands of active deals. What actually happens when you feed a massive cross-entity query like that into your standard LLM agent? It breaks. Just completely breaks. Traditional sequential LLM agents, the ones we've all been building, just cannot handle this volume of cross-entity data. They absolutely choke on it. But why they break and how BatchDAG elegantly fixes it, that's what makes this research so incredibly cool. Okay, let's dive into this. We'll be covering when LLMs break down, entering BatchDAG orchestration, going inside the architecture, the magic of entity batching, performance, cost, and accuracy, and finally, next steps for developers. Section 1. When LLMs break down. So, the current gold standard for AI apps is a sequential tool calling agent, right? It reasons, calls a tool, waits for a response, and repeats. The usual loop. But ask it to analyze those 50,000 meetings, and you hit 3 catastrophic failure modes. First up, context window overflow. If you pull just the top 25 transcript results for those meetings, boom, you're at 1.25 million tokens. That blows past even the biggest commercial context windows. Second, you lose per entity attribution. A global search might say, hey, this topic was mentioned, but it can't pin those findings to specific individual deals. And third, linear wall clock time latency. Chaining queries one by one means your latency grows proportionally with your entity count. If you're waiting on sequential API calls, you could be sitting there for over an hour and a half just to get one single answer. No way that works in production. Section 2. Enter BatchDAG orchestration. The fundamental insight here is actually pretty simple. The LLM should plan, not execute. BatchDAG is an orchestration layer where the LLM acts strictly as a planner. It takes a natural language query and spits out a typed directed acyclic graph, or a DAG, of operations. You can just think of a DAG as a one-way flowchart where steps never, ever loop back on themselves. Once that plan is locked in, a purely deterministic execution engine takes the wheel. By completely decoupling planning from execution, we get rid of that dreaded feedback loop where execution latency drags down planning latency. So how does this actually play out? It happens in 3 distinct phases. Phase 1 is planning. The LLM translates the user's natural language into that typed DAG. Phase 2 is execution. The engine evaluates the DAG using topological wave parallelism. Basically, it evaluates independent nodes simultaneously in waves, entirely deterministically. And finally, phase 3 is synthesis. This is where a final LLM call sweeps in, compiles all those aggregated results, and delivers a coherent answer with strict citations. Section 3. Inside the architecture. Now, let's look under the hood at the LLM costs for these specific operations. The BatchDAG planner can choose from 6 typed operations. And get this, 4 of them, SQL queries, semantic searches, in-memory transforms, and differential comparisons, cost absolutely 0 LLM calls during execution. 0. They run super efficiently on relational databases, vector engines, or just pure Python. It's only the analyze and fan-out steps that actually hit the pricey LLM API. So if a question can be answered with a quick SQL query and a Python transform, the system just does it. No wasting tokens on intermediate reasoning steps. Section 4, the magic of entity batching. We really need to focus on optimizing that fan-out step because, as you probably guessed, it's the most expensive operation in the whole shebang. When the system does have to analyze a massive wall of text, it uses a brilliant optimization called entity-aware batching. Let's say you have a query over 121 meetings, which comes out to about 5,800 transcript rows. The old, naive way, row-level batching, just grabs chunks of arbitrary rows at a time. That ends up creating 1,165 separate LLM batches. You're analyzing the exact same meeting dozens of times in tiny fragmented chunks. BatchDAG, instead, groups by the logical unit, like the meeting ID, before it ever fans out. By grouping all rows for a specific entity together, it creates just 25 batches. Every single batch gets the complete holistic context for its specific meeting. Section 5, Performance, Cost, and Accuracy. So what does this mean in the real world? 47x. By grouping by entity instead of by arbitrary row, BatchDAG achieves a massive 47 times reduction in LLM calls. In that 121 meeting example we just talked about, the estimated API cost drops from roughly $70 down to just $1.50, all because the system isn't redundantly calling the LLM for fragmented context. It is a massive cost saver. But hey, it's not just cheaper and faster, it is vastly more auditable. During controlled experiments on transcript-heavy queries, BatchDAG hit a 77% transcript evidence rate. That means 77% of its claims could be perfectly traced right back to the source data. That absolutely crushes the baseline React agent, which scored 60%, and an expert hand-engineered pipeline, which limped in at just 46%. This level of provenance is absolutely crucial for establishing trust in enterprise environments. And it gets better. The researchers also observed a 27% drop in hallucinations during their controlled ablation experiments. That's a huge reduction in made-up facts, and it's a direct result of how this architecture actually passes information internally. The driving design principle behind that hallucination drop is this: structured data between steps, never prose. In a standard agent, the LLM passes natural language summaries from one step to the next. But as we know, prose loses specific information. The next step has to re-parse it, re-verify it, and that's exactly where hallucinations creep in. BatchDAG completely shuts that down by enforcing structured JSON data flow between every single step. It acts way more like a real database, passing schema-validated JSON payloads that preserve the exact provenance chain from the original source straight to the final answer. Section 6, Next Steps for Developers. So how can you actually take these lessons and apply them to your own architectures today? The Dudarik.com article lays out a really solid 4-step action plan. First up, audit your current tool calling chains. Find those sequential bottlenecks where one step doesn't actually need to wait for the previous one. Second, map those independent steps to a parallel DAG structure. You can easily leverage existing workflow engines like Airflow or Dagster to evaluate them simultaneously. Third, strictly enforce structured JSON payloads between your steps to cut down on that hallucination propagation. And fourth, implement entity-aware batching. Logically group identical entities together before you fan out to the LLM to aggressively cap your API costs. It is just incredibly exciting to see how simply changing the orchestration layer from a sequential loop to a planned parallel graph can yield such dramatic improvements in cost, latency, and accuracy. It's a real game changer for enterprise AI. So I'll leave you with this to think about. Are your LLM agents currently stuck waiting in line at sequential bottlenecks? Or are you ready to step back, separate planning from execution, and orchestrate them in parallel? Thanks so much for joining me on this explainer, and happy building.